Hello everyone, welcome to the 5G Massive MIMO training. As you can see from this slide, I have summarized all the topics that will be covered in this training on the 5G Massive MIMO, and this is building on top on the previous two sessions where I already discussed about the MIMO concept in general, and the basics of the Massive MIMO, including the comparison between the Massive MIMO active antenna and traditional MIMO passive antenna. You can go back and watch these two videos if you are interested to learn about this kind of information. My plan is today, or my plan in the last 2 or 3 sessions, is to cover the first 4 parts here, which is including the introduction, focusing or including the introduction to beamforming. And this is, I will be just doing a high level recap of why beamforming in general and Massive MIMO is much better compared to traditional MIMO. And also will be sharing or highlighting what kind of channels and signals are supported by the beamforming in the 5G, especially when you compare to the 4G. Then we'll be moving to downlink beam management, which is covering all the information related to the beamforming in general for different channels, all the details theoretically and also with some practical experiences as well. Then we'll move through the beam mobility management, beam failure and recovery. Then we'll go through uplink beam management, including all these 4 parts and how beam management in general is working in the uplink direction. And related to the 5G Massive MIMO capabilities requirements, this will be already covered whenever I go through or discuss or explain downlink beam management, uplink beam management. The last 3 parts covering Massive MIMO planning, Massive MIMO antenna configuration, and Massive MIMO ad hoc topics, such as what kind of challenges and optimization opportunities for whenever you are comparing sounding reference signal and CSI-RS, or the challenges and factors impacting multi-user MIMO, and all the remaining points here. This one I will left it. I will or these topics will be left open for you. If you are interested in these topics and want me to cover them, please drop a comment so I can evaluate the demand. Based on your feedback, I can prepare 1 or 2 additional videos in order to cover these 3 parts. So in today's video, we are going to highlight or cover the part in red color here. So now let's move forward to see what we have. So before going to the first part related to the introduction to beamforming, I would like to just highlight one important point, that whatever we are going to discuss in today's video, it will be about the digital beamforming, which means related to the midband. It's not related to the milliwave. It can be applicable for milliwave as well, but you can just consider that whatever I'm going to highlight is mainly related to digital beamforming. And just to quickly recap the high-level introduction about the digital compared to the analog beamforming, as you can see from the digital beamforming, the precoder in general is done in the baseband processing part, before the digital to analog converter, which is RF chains. And we have multiple RF chains in terms of digital beamforming compared to the analog beamforming. Analog beamforming almost have a single RF chain per beam, while also the digital beamforming, as you can see here, can transmit multiple beams simultaneously. For example, here done in the same time, you have 2 beams, while this one, it's only 1 beam at a time. And this one more applicable for the sub 3 gigahertz and sub 6 gigahertz, because if you try to apply this for milliwave, so you will need to have a massive number of RF chains, which is going to increase the cost and complexity of the implementation in general. And the digital beamforming is more applicable also for multi-user MIMO. And in general, just to summarize, analog beamforming usually used for the milliwave, or you can say it also the hybrid beamforming or the analog beamforming. In case if you'd like me to cover this part in details, it's part of the Massive MIMO antenna configuration. So now let's move to the first part, which is related to introduction to beamforming. So in this slide, this will be recapping the beamforming in general, especially for the Massive MIMO. The first question I would like to ask myself: why beamforming in general and Massive MIMO is offering much better performance or efficiency compared to the traditional MIMO, even though we know that the traditional MIMO, which is starting from 44R and 8 transmission and 8 receiver, which is 88R, were also supporting the beamforming, right? So why the efficiency is much better in the Massive MIMO? As we highlighted in the previous 2 sessions, that this is related to the more antenna elements or massive number of antenna elements within the active antenna. And the more the antenna elements, the more the sharper the beams, the higher the gain, and even the better the throughput and the coverage and multiple other inputs. And as you can see, for example, in this figure in the bottom left here, this is comparing two examples for whenever you have within the antenna can see subarray or antenna array in general, 4 antenna elements and 8 antenna elements. You will see that the blue line, which is including doubled antenna elements, is showing that you have more narrower beam, which is around 10 degree, while the other one, which is the red, which is 4 antenna elements, around you have around 10 degree, which is more wider. And on top of all of that, this one is more directive, right? More directive or more having more sharper beams, and the gain almost doubled in terms of antenna gain in dB whenever you have more antennas. So that's why in Massive MIMO you have this kind of flexibility that you have a much better performance. And on top of that, the Massive MIMO in general also supporting 2D beamforming, which can supporting the horizontal domain and also the elevation domain, or vertical and horizontal domain. This is also if you would like to, for example, cover high level buildings. Also, to quickly recap why the more than 10 elements can generate a more directive beam. If you remember, we highlighted that usually between those antenna element or these antenna elements, there will be a spacing between all of them. And this is spacing whenever each of those antenna elements, for example, in this picture here, you can see that's very small. If I zoom in here, let me zoom in. The very small, like this white part here, this is related to antenna elements. So this one, assuming, for example, it have 8 antenna elements. Each one of those is radiating in the gray highlighted part here. So they will be like kind of in a constructive interference, which is building or increasing the antenna gain in the very main loop, as you can see here, and also shrinking in the side loop, as you can see here. I will add a very interesting video in the video description. If you would like really to understand and visualize this part, you can go through it if you want to get more clear understanding about how the constructive interference and why the more number of antenna elements, or why with element spacing or antenna, the spacing between the antenna elements, we're getting the gain in terms of, for example, the coverage or the more directive beams. I will be dropping a video in the video description. You can refer to this one if you'd like to get more interesting information. As a summary, the benefits which you are going to get in general for the beamforming, that you will have improvement in downlink and uplink link budgets, which is translated into better coverage. And also you will have reduced intercell interference, which is also translating into better quality or better signal interference to noise ratio. And why? Because by focusing the transmission in a specific direction, for example, like this one in this image, the focus and transmission in a specific location or direction, the beam width is relatively narrower, as you can see here, for example, on those users. So the potential intercell interference across a wide range of angles, for example, across the complete cell here, is reduced. This is the main reason why we're getting better SNR. And for the same reason, we can now support even the multi-user MIMO in more efficient way. This is the second information. The third information, the beamforming in general, that whenever the GNB, or for example in downlink direction, or UE in uplink direction, is going to calculate the beam weight in order to generate this kind of directive beam towards a specific user, it needs some particular information for the beamforming. For example, in TDD, we have this kind of sounding reference signal uplink can be transmitted by the UE, estimated by the GNB, then GNB can transmit the directive beam towards the UE based on this feedback. And the same for the something called known signal, which can be translated into CSI-RS. Those will be covered in details, but there must be an information communicated between the transmitter and receiver to be able to evaluate the propagation channel, so that transmitter will be able to evaluate where is the user direction, or where is the user direction, so how the beam is going to be calculated. So this will be covered in details in the next slide. So now let's move to the next part about what kind of channels are and reference signals supported by the 5G beamforming. As you can see in this slide, I have split it into two parts. First of all, unlike the 4G, the beamforming for downlink channels and signals supported on 5G is much more wider. If you remember, in the 4G in general, even 4G massive MIMO, it was mainly supporting the traffic beamforming, which is related to the physical downlink shared channel or the physical uplink shared channel. This is what was the mainly part related supporting in the 4G beamforming, even in 4G in general. However, the good news here in 5G, it can support the beamforming almost for all the signals and channels. You can see, for example, in the idle mode, this is supported in the SSB broadcast channel or the common beam, and also in the CSI-RS channel state information reference signal, and both of those is kind of a predefined static weight. They have a kind of fixed beams in a specific location, and this will be scanned by users, and we'll be covering this in details in the next slide. Same for the physical downlink command controller channel. This is actually depend more on the network or vendor implementation. It can be predefined static or dynamic weights, which means the beams can be allocated dynamically or based also on a predefined static weights, which means fixed location as well. But just to summarize, almost all the channels and reference signals are supporting beamforming in the 5G, while in 4G it was mainly the traffic channels which was supporting beamforming. And also we have this new concept which is called the beam management. Beam management including the beam mobility and beam failure recovery and so on, and beam failure detection and recovery. As you can see here, there is a specific reference signals will be used in beam management. In downlink direction, we have the SSB in idle mode and CSI-RS in connected mode. And uplink will have the physical random access channel during the initial access and also the sounding reference signal in the connected mode. So this is the main two important information that I would like to address here before going into details for each and every single one of those, because we'll be covering the details about all of these channel reference signal, how the beamforming is being implemented for all of them. And next slide as well. So this part about the beam management or beamforming life cycle, as I have mentioned here in the top right here. Actually, this just summarizes the overall procedures being followed by even the network or the UE until they acquire or receive the allocation of the traffic channels. Actually, the primary objective of beam management in general is to identify and maintain the optimal beams for transmission in both the uplink and downlink directions. Especially, like you can say, beam management is mainly applied to both the physical downlink shared channel and physical uplink shared channel. This is the end goal of the beam management, that you will follow multiple steps until you got the optimal traffic channel beams for even in uplink or downlink direction. So as you can see here in this sphere, I just highlighted that initially, whenever the users or the UE or device is in the idle mode, you will be starting in the idle mode. So the first thing will happen from the network and the U side, that as you know, the first thing is done usually in the 5G, the user will be starting scanning the scanning the network, for example, scanning the synchronization signal and primary synchronization signal and secondary synchronization signal until he acquired so-called SSB, right? But this is how it's happening. So if you look into this figure on the left side here, this is something called initial beam acquisition, which is usually called procedure P1, okay? During the P1, and during the initial access and the idle mode, the network will be like transmitting a different SSB beams within the cells up to 8 in the mid band, which is up into eight SSB beams, which is being covering the complete cell, as you can see as an example here. So the first thing will be done from the UE. He will start scanning all these SSBs in that time domain and trying to measure all of them until he finds the best and optimum beams based on, for example, in the coverage, RSRP. So once he obtained the best beams, the network still doesn't know which beam is the best for the user, because this is something done by the user itself. He finds that, for example, here in this particular example, the beam number 3 or SSB beam index number 3 is the best beam for the user. So how the network will know and how we'll have this same, the so-called something called beam pairs. Beam pairs means, which is highlighted in the top right here, which is the second step actually. Beam pairs meaning what? How the network or the GNB side will know what is the best beam in the downlink direction towards the UE. So In the very beginning in the idle mode, once the user acquire the SSB or synchronization signal block, he will be reading the system information block type 1. So he will get some information about the RATCH. And each SSB block is associated with a specific preamble ID. I will be explaining this part in details with a visualization example in upcoming slides as well. So uh, as I mentioned, because the user already read or decoded the SSB, he will know the system information block type 1. He will acquire some information about the random access procedures. So the next step that user will initiate uplink random access preamble, and based on the preamble, because the GMB know that this preamble is associated with a specific beam, so the GMB will know that the user was already latching or camming on the SSB block ID 3. So this, in this case, the network and the user side establish the best downlink beam and even uplink beam. Downlink beam pairs means that for example, the best beam here is downlink, is number 3, and for example, received in the downlink direction by SSB beam index 2 from the receiver side, from the user side. And also in the uplink direction, the initial BRATCH will be sending an uplink. So this would be the uplink beam for the user. And in this case, we had established both beam pairs for both uplink direction. And example for the beam pairs, as you can see here in the bottom left figure here, that for example, this is the transmitted beams from the GMB side. And the user has identified that this is the best received beam here, and all this information is communicated during the SSB acquisition and also during sending the BRATCH and uplink from the user side. This is the main idea about the initial beam acquisition, which is covering the part related to the so-called beam sweeping. And beam sweeping, whenever you hear this terminology or this kind of word, the beam sweeping, this is mainly happening in the idle mode, and it's more related to the SSB, which is being transmitted by the cell in different beams covering the complete cell. But one important point to highlight that in general, this is not a mandatory deployment for all the network or vendors. For example, some vendors might have the initial beam as only one beam. For example, the SSB can be only one wide beam, or even you can change the configuration. This is based on the practical scenario. In any vendor, they can use only one wide beam. So in this case, it's already one wide beam, so there is no beam sweeping. So it will be just straightforward. Whatever beam is there, the user will be coming this beam, and this is also reducing later on the kind of the beam switching between different SSBs. But as per the standard, this should be the scenario during the procedure P1 initial beam acquisition P1. This one will be showing the beam sweeping, and you will achieve this kind of beam bearings through the user sending random access response and uplink. So once the second point being done, which is the beam bearing, and the user already transited to the connected mode after sending the uplink or BRATCH in the uplink direction. So now the GMB will start doing something called beam refinement. Beam refinement means that, as you know, in the connected mode, the user will start be measuring the so-called CSI-RS, which is a channel state information reference signal, and he will be start measuring that part in order to give some feedback about the downlink propagation channel to the GMB, to give him based on the measurement of the CSI-RS. So actually, during the CSI-RS, the GMB, as per the standard as well, can do additional refinement for the initial beams. So for example, if you look into the same figure on left here, there is P2, which is a beam refinement, P2. This one actually, as you can see here, each of the SSB beams will be refined into four small beams, as you can see. Those beams is more related to CSI-RS. So now, for example, if you have 8 beams in the cell, as shown in the bottom left figure here, you will have around 32. 8 multiplied by 4, you will have around 32 beams, CSI-RS beams within the complete cell. So it will looks like this at the very end for the complete site, which is 3 sectors. We'll have very small beams for the CSI-RS. This is called beam refinement, and this is required that from the connected mode, so you will have more narrower beams. So whenever the user is going to read the CSI-RS, he will have more accuracy and also less interference, so he can give an accurate feedback about his downlink propagation channel, in order to later on the GMB will use whatever information acquired by the user to start doing the allocation or the dynamic allocation of the shared channel or traffic channel beams in general. So this is P2 related to the CSI or beam refinement in general. And again, this is based on the standard, but this is not really implemented practically in the current scenario in majority of the networks. You will hear that, okay, each SSB beam should have 4 CSRS, but this is not the actual scenario now, at least as per my knowledge. This is as per the 3G PEP standard. Yes, this should be the scenario, but at least for the mid-band, it's not yet implemented. You'll find that, yes, you have a pre-coded CSRS beams or a beamforming for the CSRS, but it's not really following the exact scenario. I'll be covering this part in the next slides as well. The third procedure here, which is I didn't highlight in this one because this would be more about related to the E capability itself. Maybe it's in milliwave, but it's not yet now in the mid-band part. That the UE himself, P3, the UE himself will do this kind of beam swapping in order to change the received beam. So based, like for example, if he foresee that this beam 2, the best received beam should be 1 or 3 or 4, he's doing a beam swapping from his side in order to achieve the best received beam, for example, in downlink direction. So this is like a procedure is not yet available in the mid-band, as I mentioned. So this can be there in the future, later on, even in the milliwave or whenever we have devices supporting this kind of beam swapping, as you can see in this figure. So once the beam refinement is being done, which is the CSI-RS beam format, the user now will start measuring the CSI-RS, and he will start reporting some information to the network in order to the network to allow the network to allocate the best beam or the traffic beam, which is PED SSH or physical downlink shared channel, or if you're speaking about uplink direction, it will be physical uplink shared channel. So this is actually can be done through different methods. If you are speaking even about both of them, even based on CSI-RS, which is a cell-specific channel state information reference signal measurement. We'll be covering this part in details, which is kind of called code blocks and downlink direction or sounding reference signal. So this feedback will be reported to the GNB. So GNB will decide based on this report what is the best beam to be allocated as a direction of the users, and it will give an error beam. Also, will be showing this in details. So once the feedback is being sent and so on. So the next procedures, it's about the beam mobility management. For example, as we highlighted in the previous scenarios, you might have this kind of, for example, during the SSB scenario, you have 8 beams. So you might switch from one beam to another. So you need to do this kind of beam switching, right? You need to change a beam. It's called beam switching, especially whenever you are speaking about changing within the intracell. So there is 2 types of beam mobility management. Something called intracell mobility, which is actually done during only by the L1, L2 procedures, which is done as a communication between the physical and MAC layer only. There is no involvement of the RRC layer, which means there is no interruption here. This procedure is being done whenever the user is just deciding to shift from one cell to another. He will be reporting to the network something called CRI or SSB RI. CRI is referred to CSI-RS resource indicator, and this is one SSB resource indicator. In other words, like for example, each SSB, for example, if you have 8 SSB, each SSB will be associated with a specific index. So if the user, for example, changed his location from SSB 8 and he moved to SSB 6, he will be reporting to the network, I'm coming now in SSB 6, and this is my L1 RSRP. There is L1 RSRP and there is L3 RSRP. This is like reporting the coverage about his current situation. So this is actually the call, so that as mentioned here, the base station and UE will adapt the beams to changing condition, and this is intra-cell mobility involves beam switching. And for the other way around, if you moved from one cell to another or from one side to another, this is just involving the normal procedures of the handovers, as we have seen before, and even in the 4G or any other, or even in 5G, which is related to the A3 or A2 or A5 reporting, dependent intra-frequency or inter-frequency handovers. This would be kind of a normal one. I'll be covering both scenarios with details with parameters as well. Then moving to next part, it's about the beam failure detection and recovery. Okay. First of all, this is will be happened whenever you have, for example, assume you have this kind of beam switching from one CSI-RS beam to another, and this beam switching was being failed, right? So this can trigger that there is a beam failure detection. This is will be detected by the user. There is a beam failures. Also, I have details explanation about that part. So in this case, if the user detected there is a beam failure detection, for example, this can be done at the physical layer and MAC layer as well, without involving the high layer, and it's very transparent to the RRC layer. So if it's being detected at the MAC layer that there is a beam failure detection, the user will initiate the beam recovery through initiating the PRATCH procedures toward the target or the new target beam. So this can be acquired at the very end. And in general, the radio link failures in general in 5G can be divided into two parts, which is beam at the MAC layer or RC layer. Currently, the MAC layer, which is related to the beam failure detection and recovery and so on, this is not yet very applicable currently in the current deployment in the midband, as you saw. You may find it, but I'm telling you from my practical experience, it's mainly about the normal radio link failure, which is related to the T310, as I will be explained later on. I will explain the reason why later on when you go into details for that one. But this is just a slide summarizing the overall procedures for the beam management, starting from the idle mode until you got the traffic channels, and even if you have kind of changing your SSB or CSI-RS, will have this kind of beam mobility, and also if the beam is being failed, or in general if there is a radio link failure being triggered. So this is just explaining the complete procedures for the beam forming within the 5G. So here, before going to all the beam forming types, SSB and CSI-RS and all the others like separately, I would like to discuss the beam forming types in general as a high level concept in the 5G. There is something called Eigen-based or Grid-of-Beams. Okay. This, as you can see, I can see Eigen-based or EBB. This one, as you can see in bottom left here, this is just based on the sounding referencing. It's very simple, as you can see. For example, here, this one, it's the user was at the time one. This is the same user, but just moving. Here he's reporting in the uplink the sounding reference signal. So based on the uplink direction, because we are assuming there is a channel reciprocity, which is for the TDD. For example, as you know, that time division duplex, the frequency in downlink and uplink direction are the same. So this means that the unit GMB can estimate the downlink channel propagation after evaluating the SRS feedback. So GMB will be measuring the transmission of the sounding reference signal uplink, and based on that, it will decide the pre-coding matrices, and which means that it will decide the user location or angle of arrival, and it will decide the allocated physical downlink shared channel, and it will, as you can see here, it will estimate all the downlink propagation channel based on sounding reference signal. Then it will be transmitted the physical downlink shared channel in the downlink direction here. Same once the user is being moved, assume that he changes location, he's still being reported periodically the sounding reference signal and uplink. So GMB will do the estimation for the downlink channel propagation, and based on the estimation, it will initiate the new physical downlink shared channel and downlink. So as you can see, I had summarized it here in the top here. So this is actually dynamically updates the beam forming ways to track the U movement once you move from here to there. And this is mainly suitable for TDD, which is actually using this kind of concept which is called channel reciprocity, as I just explained. And based on the SRS uplink measurement, the GMB will derive the downlink weights, and based on the downlink weights, it will start doing this kind of physical downlink shared channel direction or send it towards the specific user. Now, the second types of beams which we have in the 5G in general is called Grid-of-Beams or GOB. Okay, this Grid-of-Beams it's have two different types. It can be beamformed or non-beam formed. Okay, for example, here I'm giving a very simple example as a set of beamformed. The first one for the Grid-of-Beams, set of beamformed CSI-RS or SSB. Here I'm giving the example about the synchronous signal block, which is SSB. As you know that the SSB can be transmitted in a fixed directions or a static location, or have a static weight covering a specific cell, as you can see here, for example, here. So in this case, what will happen? The user will be measuring, as we explained in the previous, all the SSBs, and he will acquire which one have the best coverage. And if in connected mode, he will be reporting whenever he move, for example, from this SSB to the second SSB, as mentioned here, will be reporting the something called SSB-RI, which is SSB resource indicator, telling him I moved, for example, from beam 0 to beam 1. So now he was telling the network I changed my location from here to there. This is based on the grid of beams in a fixed and static location, as you can see. This doesn't have any like dynamic change, but at the end it's beamformed. Beamformed means that it's having not wide beam, it's having multiple narrower beam covering the complete cell. That's why it's called beamformed, but have a static weight. This is the first part. So the user will be switching between both of them through sending a feedback. And the same can be applied whenever you have also multiple CSI-RS. In case of CSI-RS is being beamformed, you have multiple CSI-RS in connected mode, and also the user moved from one CSI-RS to the second one, you will be reporting something called CRI, which is stand for CSI-RS resource indicator, telling him I was camping on CSI-RS, for example, beam 1. Now I move to beam 3, beam 4, or whatever. And also the user will be reporting something else called RSRP L1, telling him what is the current of coverage he's obtaining whenever he moved from one beam to another. So this is a grid beam. The third type, actually, it's called a set of non-beamformed CSRS. Okay, as you can see, non-beamformed grid of beams. And this is, for example, the CSRS itself. It can be transmitted as a wide beam without any beamforming, like without any pre-coded values. So it will be transmitted as a wide beam, and it might be matching with, for example, SSB can be also wide beam, can be matching with the common channels or whatever. This is a different deployment as well, which is existing as per the standard. So the CSRS can be in general a wide beam without any beamforming, no narrower beams, and so on. So based on that, the user would be just measuring the CSRS and downlink direction, and based on this one, he will be acquiring the so-called PMI. PMI, as you can see, this is pre-coding matrix. The user will be reporting this one just to tell the GMB what is his kind of angle of arrival. I'll be explaining about what kind of information being reported in a PMI, which is part of the so-called CSI, channel state information, which is covering also another multiple information such as CQI, rank indication, and also covering these parts which relate to CRI and SSBRI. I will be explaining this part in a very detailed in the upcoming slides, but just keep it in your mind that we have currently two types of beamforming in 5G, which is called Eigen-based, based on the channel reciprocity, based on SRS, the first one here, or the second one, which is called Grid-of-Beams. And Grid-Beams, this is based on a fixed set of beams positions in a fixed location, and this is also can be divided into two types, even beamformed or non-beamformed, as we have just explained. Next, we'll be covering now each of the previous mentioned procedures, including the SSB, CSI-RS, then how we acquire the shared channel, traffic channels based on, for example, SRS or CSI-RS. This will be explained one by one. Also, we'll be covering the PDCCH or physical downlink command control channel beamforming as well. So we'll go through one by one to explain with more details. So here, as you can see, here we'll be explaining the first part related to the initial acquisition, which is P1, which is during the idle mode, which is based on SSB or the so-called beam swapping and procedure 1. Okay, if you remember the previous figure here, we're covering this part. So let me now explain what will happen, how the communication is being exchanged between the JMB and the UE. For example, as you can see in the very initial axis, here, the GMB will transmitting something called SSB burst. Okay, SSB burst. This is including how many active beams you have. For example, how many active beams and what is the timing of each of those beams. For example, here I highlighted that we have 8 SSB beams. So this SSB burst, I will be showing also from the traces during the mobility board, what kind of information you can see, for example, in the system information block type 1 in 5G standalone. You will assign B as, for example, bits. up to 8 bits. Each one, if it's all 1, this means you have 8 bits. All of them is 1. This means you have 8 active SSB in the time domain. And if you can recall in general that the SSB can be transmitted in a fixed location, but it's being transmitted in different times. For example, within the initial 5 millisecond, initial 4 slots, all the SSB will be transmitted. But the user will be measuring all of them. So initially, the GMV will be transmitted this SSB burst. It will be acquired by the user during the initial access through reading the system information block type 1. Then the user will start doing the measurement. He will read all the SSBs until he finds which one is the best beam. And after also within the same system information block type 1, there is information about the RACH resources. This is actually telling the user that, for example, this SSB is associated with, for example, SSB 0 is associated with PRACH 0, 1, and 2. And SSB 3 is associated with PRACH 9, 10, and 11. So, for example, here the user, after reading, he found that the SSB 3 have the best radio condition based RSRP. So he will decide that this is my beam. This is the one I should receive in the downlink, and he will camp on this one. So in order to complete the uplink synchronization and to get into the connected mode, afterwards, the user will initiate the so-called RACH or RACH preamble. So now he knows that this is the best beam, which is SSB beam index 3. He will initiate a preambles using any of those, 9, 10, 11. So the GMB will know what this one is being said, that based on that, on this preambles ID, it's already know that this one is associated with SSB block 3. So the GMB and now will know that this is the beam is just serving the user. So it will now identifies the beams for the subsequent downlink and even uplink transmission. Why uplink transmission? Because also the BRACH will be used as uplink beam, the initial uplink beam for the user. So based on that, GMBU now will know that the best beam in downlink is SSB beam 3, and based on the RACH preambles, it will know his also best uplink beam as well. So this can start now getting into connected mode and move forward afterwards, and this is how the initial acquisition is being happening. Again, I have to stress into this point. As you can see here, each frequency range have a maximum, as per the standard, a maximum number of SSBs. For example, up to 3 GHz, you have 4 SSB beams. Also, 3 to 6 GHz, you have up to 8 SSB beams. And for milliwave, you have up to 64 SSB beams. And again, also to stress onto this point, this is just as per the standard, but it can be again, for example, initial beam acquisition or initial beam selection can be a wide beam at the end. So you will see this one, for example, at the end, just only one active beam because it's wide. You don't have 8 beams at the very end. So the user doesn't need to, for example, decode all that part. And for example, one of the advantage of having a wide beam that you will have less access time. But at the same time, also the narrower beams will give you more advantage in terms of sometimes the quality or even the coverage. But again, this is all of them is kind of a trade-off. So this is all about the first procedures SSB, which is the initial beam acquisition. The second part here, it's about the beam refinement or the CSI-RS based transmit beam refinement procedures 2, which was the second or third point in the very beginning, as we highlighted, called beam refinement B2, which is actually usually this is after establishing the initial beam, which is SSB, initial acquisition. After establishing this one, a finer beams is needed for high gain unicast transmission. For example, the GMB will decide that it might need now to do more refinement for the beams in the connected modes. So for example, now it will decide, I would like to have to transmit a different CSI-RS in different directions, as we highlighted before, which is called Grid-of-Beams, but in terms of CSI-RS. Those is like would be beam format CSI-RS. So for example, in here, I'm assuming that the SSB have for CSI-RS, but more narrower compared to the SSB here. So as you can see, for example, each one of those is associated with a CSI resource. I will explain this one later on. So again, the user would be measuring all of them, and he will be selecting the best one based on the RSRP. And after selecting this one, he'll be able to even do some kind of feedback into the GMB in the uplink direction to start the next procedures related to the dynamic, the traffic channels, as we are going to explain. So this is again related to the beam refinement, which explained in the very beginning as well. So the beam refinement, as I highlighted, if you read the bottom left figure here, it's saying that the CSI reference signal beams, this has helped to refine the beam selection by offering higher resolution than the sequential signal block. For example, simulation signal block, for one beam, it was kind of more wider. So now we have higher resolution for the CSI-RS. And each SSB beam block, it can have up to 4 CSI-RS beams. So if you have 8 SSB beams, this means you will have 8 multiplied by 4, 32 in the complete cell, as we highlighted also in the very beginning. And this is as per the 3GPP standard, but it's not necessary to be implemented by the implementation or network implementation. And in general, more beams you have, this means you have fewer coverage gaps, and this improves the performance in general. This is as theoretical point of view. So now let's move to the next part. So the next part, actually, I'm going to discuss about how the traffic beams are being allocated from the JMB side in the downlink direction, or even from the UE side in the uplink direction, which is PDSSH or PUSSH. Okay, this is how it's being done. As you know, in downlink direction, will be our main topics being covered today. We have two different methodologies or methods, which is to allocate the traffic beams, which can be based on something called codebook-based, which is the bottom down here, which is based on some reporting in the uplink, which is called PMI, and this is pre-coding matrix and uplink direction through the user will be reading the so-called CSI-RS. As you can see here, for example, in this figure, there is a downlink transmission here, and this is using the CSI-RS. The user will be measuring here, then he reporting the uplink, the so-called PMI. And also the other type, which is called the reciprocity based, as we highlighted earlier as well. This is based on uplink transmission. The user will be transmitting uplink SRS, and assuming there is a channel reciprocity, so the GMB directly will be estimating the downlink channel propagation, and based on that, it will be defined the best pre-coding matrix, and it will send the physical downlink share the channel towards the users in a specific direction with a specific, for example, narrower beams and so on. There is some shortcomings about both of them. For example, the shortcomings for the SRS, that as you know, this is at the end it's uplink direction, so this is have a limited coverage because of the UE limitation. Also, it requires a specific capability. For example, it requires something called antenna switching. I would be discussing this part as well whenever we go to the SRS part, because we'll be covering both of those in details now. Also, this it's coming sometimes having a SRS resource availability, it might be limited if you have a very high number of connected users. But it's, even though this is considered as a shortcoming, but as a performance point of view, this is as a resource or capacity point of view, this is even offering better performance in terms of capacity compared to the codebook, which is have a finite or limited number of pre-coding matrices, as I will explain later on. The codebook-based means that the GMB itself will do kind of a pre-coding matrix to maximize the signal-to-noise ratio, so it will identify a vector of codes which will be transmitted and carried on the so-called CSI-RS whenever the GMB is transmitting the CSI-RS in downlink direction, and the user will be able to decode the best pre-coding matrix and report it back to GMB in the uplink direction to tell him, this is my location, I need this particular beam. So the GMB will dynamically allocate based on the PMI feedback, which is being decoded based on CSI-RS. So the codebook in general, we have two different types. Actually, it's three, but the most common is type 1, which have two different types, something called single or multi-panel. Single panel means that your antennas only have one panel. Multi-panel means that your antenna have two different panels. And the most common scenario now, you have a single panel. So forget about the multi-panel for now. So this is just explaining how this part is working, but this is usually mainly working during the single user MIMO. Okay, and This also kind of have a partial UE capability limitation, because as I will explain later on, this has a kind of relation to the maximum number of supported CSI-RS ports. This one I'll explain with the configuration in details for each of those types, for the type 1 single panel and type 2 single panel. Type 2 or codebook type 2 single panel, this is actually more appropriate for the multi-user MIMO, intended mainly for multi-user MIMO. However, the maximum rank can be rank 2. Also, this is because it's supporting multi-user MIMO. This is kind of have much higher overhead, because the user need to report additional information on uplink to allow the multi-user MIMO, to allow the GMB to do this kind of beam phasing or beam amplitude, as will be explained later on. Also, this require a UE capability. The UE must be supporting the type 2 single panel. I will explain how to check in general all these kind of capability information, even for the antenna switching and the SRS, or the CSI reporting number of ports, maximum number of ports supporting by the user, or even by the panel itself, house beam. So this will be explained later. But just was to give you a high-level introduction. Now we'll go through all these types now, which is type 1, type 2, and SRS. And the end goal of all of that is to obtain or require the traffic beams, the best traffic beams in the downlink direction. Here we are speaking about the downlink. Let's move forward. So the first part I'm going to cover is related to the codebook-based, like acquiring the traffic beams based on the codebook-based. As highlighted, currently the main used codebooks is codebook type 1 and type 2. But also we have an additional types, which is related to codebook enhanced type 2, which is enhancement for the type 2, because type 2 is offering much very high overhead. So this enhanced one is kind of advancement for or enhanced version for the type 2 in order to offer a less overhead, and even it's offer more spatial separation between the users, and even it's better, offering much better performance for the multi-user MIME. This is like introduced in release 16 and 17. The first two I already explained in the previous slide. The one which is coming in release 17 and 18, this is actually as promising for future, especially for 6G. This is based on AI-based feedback. This is kind based on uses a machine learning models to improve the beam selection and MIMO scheduling in general. And this is also because it's having a learning model, so it can reduce the feedback and overhead by learning the UE behavior. And this is still in the early research development phase. And for example, this one, instead of sending large PMI feedback, that you can send a compressed AI-generated feedback vector for faster beamforming updates. This can be something in the future. The most common two which we are going to discuss today, which is codebook type 1 and codebook type 2. We explained this part, was also supporting them with IUE logs as well. So let's move now to the details about these two types and see the very interesting information. Next slide. So the first type I would like to start with, which is related to the codebook type 1, which is used during the traffic beam allocation, which is referred to the PDSSCH, physical downlink shared channel allocation. What kind of beam can be allocated for the physical downlink shared channel to the user based on the codebook type 1. So first of all, the word codebook, what it means. Actually, the meaning of codebook under the context of the CSI-RS, channel state information, channel state information reference signal, is a set of pre-coded or pre-coding matrices. If you look into this complicated table in the bottom left here, this is actually something you can configure from your network side. For example, in the network, you can give two inputs, and based on these inputs, you can define how many codebooks we have, which these codebooks define a particular beams, which can be later on being decoded by the user in the downlink direction through reading the CSI-RS, and he will report back to the GMB telling him that this is the best pre-coding matrix for me, which can maximize my signal to noise ratio. So initially, from the configuration point of view and the network, in your network, what you need to do, you need to select any of those configuration. Here, as you can see here, we have something called as per this 3G PAP table. You can see that we have something called number of CSI-RS antenna ports. So first thing, you need to define how many ports you would like to read. And if you refer to my previous videos about the CSI-RS channel, You can refer to my channel, you find this video. This like each of those ports can give you more granularity, and also whenever you add more ports in the downlink direction, for example, this means the user will be measuring more reference signal downlink. So for example, assume that you brought the configuration to 8 ports or 32 ports. Okay, this means you will have 32 CSI-RS reference signal in the downlink direction being transmitted from GMB towards the user, and the user will be reading the 32 downlink direction. This is the first input, but till now we didn't define the predefined precoding matrix, which is called the codebook type 1. So how it can be defined? The second configuration you can give from the GMB side. This is like something configurable. So first one was antenna board. Second one related to this N1 and N2, and this is like kind of defining the antenna pattern, or how kind of antenna your antenna will be operating. Let me an example. For example, N1 and N2. This is like determine the number of antenna in horizontal and vertical plane. Okay. For example, here you are telling them that I need to have two antenna in the horizontal plane and one on the vertical plane. And for example, the second one here is 2, 2. It's showing that you will have 2 in the horizontal and 2 in the vertical plane as well. So this can give more advantage whenever you would like to improve any of the vertical, for example, more high rise building or whatever. So you can go for the second configuration, because this is giving more advantage to the vertical plane as well. And as you can see here, we have also something called O1, O2, which is called oversampling. This is like as if you multiply it, for example, 2 by 4. This means you will have 8 beams in the horizontal plane, and you will have 1 beam in the vertical plane. While here, 2 multiplied by 4 and 2 multiplied by 4, you will have 8 in the horizontal and 8 in the vertical, and so on. If you keep doing the same here, and in total you will have 8 beams. Here in total you have 64 beams, and this is your precoding matrix. For example, here the user will tell them, I would like to select, he have 8 options in the horizontal plane, which he will be selecting any one of those based on his location, and he will report back to the GMB telling them that my best, for example, horizontal direction is, for example, number 1 or 2 or 3. I will be explaining this also in more details in the next slide. Same for the other directions. So the first thing you have to do first of all, you need to configure what kind of settings you would like to configure to your network, and this is dependent on the scenario. For example, if you like to improve the areas with high level or high rise building, so you need to look into a configuration which is improving your vertical plane. For example, let's assume 32 ports and 8 and 2. So 8, 2, this means you have 2 vertical plane. So you can now have more control over controlling the beam over the vertical direction or elevation direction. So this is like 2D. So you can choose this one. In case, for example, you don't have any high-rise building, assume that it's a flat area. So you can now go to the configuration 16.1. Why? Because whenever you increase the number of antenna in horizontal plane, this means you will have more sub-arrays in the horizontal plane. This means you can have even much better coverage and also much better granularity in terms of the beams and downlink direction. For example, in this scenario, you have 16 multiplied by 4, you have 64 beams. This means you will have more narrower beams. This means you can even achieve much better signal to noise ratio, or maximize your signal to noise ratio for the users. So this will result in more like a much higher granularity if you selected the 32, for example, scenario and 16 by 1 for the horizontal direction. So this can have a much better performance. Keep it for now. I know it's kind of looks complicated, but next slide also, next 2 or 3 slides will explain with a very good visualization example. But let me explain in general. Once you set your configuration, for example, assume you selected any of those configuration, assume you selected any of those configuration. Now you would like to understand in general how this kind of information is being transferred or sent from the GMB to the user, and how the user will be selecting the best beams out of all of these matrices. As you can see, this is at the end, this is your codebook. For example, here you have 8 codebooks, you have 64 codebooks, you have 256 codebooks or 256 beams, which is 32 in the horizontal and 8 in the vertical. So the user need to select the best out of all these beams to tell the GNB this is the best beam and this is my angle of arrival. I would like you to start transmitting my traffic beams toward this particular direction. So this is how this is being happening. If you look into the bottom right figure here, initially this is the total beams at the GNB sites. As I told you, this will be defined based on the configuration you are giving here. CSI-RS configuration plus N1, N2 plus O1, O2. And this is something configurable. You can control it from the GNB side. So for example, here you can see this is the total GNB, and this is all the matrices, which is the recoding matrix in general referred as W. W is a product of W1 multiplied by W2, and W1 usually is called long term because it's being updated every 100 millisecond, while the W2 is called short term because it's kind of related to the phase change, which is a short term, which is updating every almost 1 millisecond. So in general, as you can see here, already the total GNBs is here. Then the W1 will be selecting, for example, 4 beams, which is starting from B0 till B3, assuming that this is a BI, beam indication I, for example. And you have the W2. So the user now will need to select the one beam only, the codebook type 1. The user need from codebook type to select only a single beams out of those 4, and it need to tell the network which beams is the best for him. For example, here I selected this one, and also it need to tell the network what is the co-phase he would like the network to steer the beam towards. Like for example, what is his direction or whatever. So the user need to select the beam and the co-phase, which is here referred as VI and alpha as well. Okay, so once the user select VI and alpha, he report these two information in the so-called PMI pre-coding matrix and uplink direction. So once it's being reported, the GNB will do the calculation based on this matrix. So it will understand, for example, now the user need this. The user need to be allocated for the physical downlink shared channel based on this pre-coding matrix, based on these two factors. And just a side note, sometimes the network will decide not to allocate the beam in the reported information. This depends also on the network implementation, but sometimes the network will see that no, this user need to be allocated another PMI or another pre-coding matrix. But this is not the case for the meantime. So just to quickly again explain, here, for example, once you did the configuration, assume now you have the CSI-RS being transmitted as a wide beam. I'm assuming here the CSI-RS is being as a wide beam. Sometimes it can be also, as I mentioned before, 4 beams. This is again based on the configuration. For example, you can select 8 ports, and you have another 4th parameter called, for example, in different, depend on the vendor, but let's call it, as I'll explain later on as well, called CSI resource ID, for example. It's telling him, as a configuration point of view, you are saying that I need only 8 ports to be transmitted in downlink direction. And I need also this to be like being beamformed. I need to do a beamform for CSI-RS. So instead of 1 wide beam, I need to have a 4. So you can configure this CSI-RS resource ID into 4. So this means this one will be 4 wide beams. Okay. So here, all of these is the gray one is the predefined code matrices, which where the user need to start measuring the CSI-RS, as you can see here in the right figure here. This is, I'm assuming this is 8 ports. So we have 8 CSI-RS reference signal, non-zero power reference signal. So the user will be measuring this one. And based on that part, he will define the best combination, which is the best beam, BI and alpha. And he will be reporting back the so-called PMI, which is the CSI channel state information. This one including the UE feedback, CQI, PMI, and RI, which is the rank indication as well. For example, here is telling him I have something called PMI 11 and PMI 12. Those PMI 11 and 12 are 3 and 1. So it's telling him this is my horizontal and vertical beam, and also this is my co-phase, or this is a phase. So based on this feedback, for example, the GNB will know that this is his direction. So I would like, for example, to allocate this particular beam here, which is called physical downlink shared channel, based on this particular feedback. And now the user will be start like doing his download normally and so on. Now let's explain more about this part related to N1 and 2 and O1 and O2 with more example, which is will be showing a visualization example just to try to make more comprehensive understanding about it. And just last thing here, you can see the bottom down table here, just summarizing the steps followed during the codebook type 1. For example, after the initial beam generation, which is related to, for example, SSB or whatever, then there will be the W1 and W2. The user will be selecting during the W2, the BI and alpha. Then it will be sent this one through the PMI report. So the transmitter, which is the GMB side, will be applying this BI and alpha and send the final transmission, which is the physical downlink to the channel. So going back to this configuration, and also I would like to highlight an important information about kind of the differences between the configuration if you would like to do some trials in your network. So again, as you can see here, I just highlighted the exact same table in the previous slide, okay? But here I'm trying just to give a more visualization. First of all, assume that you have 8 ports, okay? You only configure 8 ports, and you decided to give this N1 and N2 as, for example, 2 and 2. So this N1 and N2, this will be like converting into a logical port from the antenna point of view. And by the way, there is something called P2A, which is port to antenna mapping. This port to antenna mapping, I will explain it, and if you would like me to do so, you can confirm in the comments. I'll consider from high level view how the port mapping is being done to the physical antenna. But this is, again, it's different. Each network implementation or vendor can follow different methods, okay? But there is a high level understanding about it. I can explain it later on as well. But just you logical. 2 means what? You can see here you have two. Let's first start with 2-1. And 2-1 means you have 2 in the horizontal, this 1-2, and you have only 1 in the vertical, as you can see here. Okay, and 2-2, this means you have 1 and 2 here, like you have 2 in the horizontal and 2 in the vertical, 1 here and 1 here. And this is 4 and 1. You have 4 in the horizontal, 1 2 3 4. Okay, and you have only 1 in the vertical. The 3-2, you have 3 in the horizontal, 1 2 3, and 2 in the vertical, and so on here. For example, in 4 and 4, you have 1 2 3 4, 4 in the horizontal and 4 in the vertical. And the more you increase the vertical, you might have reduction in horizontal, so you can improve your vertical plane coverage, but you can, for example, degrade your horizontal plane coverage. So you need to be really careful for the configuration point of view. Okay, regarding the CSI-RS ports, this is, as you can see, it's having a kind of controlling more about the CSI-RS itself, like how the CSI-RS is being transmitted. So, for example, assume now you selected, let's see, CM32, and assume you have this one as non-beam format, as a wide beam, okay? And here you selected another scenario as 8 ports, but with 4 beams, as an example, which means narrower beams, okay? So what is the main difference between them? This one is giving more granularity. As you can see here, in that part, you can even achieve more traffic beams for example, in this configuration, you have up to 256, which is up to 32. So this is giving more granularity in terms of the traffic beams. You have more narrower beams, okay? But again, this is associated with some drawbacks. It might be a drawbacks, depending on the scenarios at the very end. For example, you have more overhead because in each transmission, the user need to read or measure 32 CSI-S reference signal in the user plane. But again, increasing that part, yes, it's increasing the overhead, so it can impact your maximum downlink throughput. But at the same time, giving more estimation, this is giving more granularity to the user, so he'll be decoding more CSI-RS resources. He will he will provide more accurate feedback, and also he will have more pre-coding matrices to select out of them, as you mentioned here. So this is the first part. So if you make it as a wide beam, first of all, because it's 32 CSI-RS, this means your sub-arrays will be, you will have a less sub-arrays transmission, which means less antenna elements per each of the port transmission. So this means you might have a less coverage compared to the 8 ports. Because 8 ports, if it's beam format, it's having 2 advantages in terms of coverage. It can go even to higher distance, not necessarily to cover a wider area, but to go for a larger distance. Why? Because 8 ports means that you can have 4 CSI sources, you can have 4 wide beams, and in the same side, this means you will have more sub-arrays and more antenna elements transmitted per each port, because now you will the physical or the antenna itself will utilize the existing 64T, 64R or the antenna elements in there to just utilize it for 8 ports. Yes, it will be transmitted in different timing and so on, but at the end the user only need to measure 8. So this can also provide again in the coverage in general of the CSI-RS, and also can go larger distance. But again, can be compensated in the 32 ports through doing power posting using the CDM or FDM. This can be also detailed about the CSIs in general. And one more advantage that here you have less overhead, right? So you can achieve maximum higher throughput. But again, this have a less granularity. So this is, you might end by that you have more wider beam in terms of traffic beams and so on. So if you're going to translate this one N1, N2 into beams, as you can see here, this is example is I can see it's perfect example. I have quoted from Massive MIMO for new radio from Samsung white paper, as you can see here. If I zoom in here, so here, for example, let me just zoom out a little. Okay, so for example, in this example, as you can see here, it's highlighting NV, OV, and in the horizontal plane, it's having NHOH. So NHOH is referring to N1 and O1, and NVOV is referring to N2 and A2. This means that it's representing how many beams you will have in horizontal plane or vertical plane. So now assume that here you have whatever configuration you have mentioned here. So for example, you will multiply in H by OH. So assuming here you have this scenario. So assume this will be 32 beams in the downlink direction, and VOV will be selecting 32 beams in the vertical direction. And the user will need to select only one out of those beams in one direction, and one horizontal and one vertical. Assume now the user will be selecting this one. So he will be reporting the PMI I11 at about the horizontal plane. I will also explain this one with a visual example in the next slide. And it will be also reporting the PMI I12, which is, for example, in the vertical plane. So telling him this is the best beam for me in horizontal plane, and this is the best beam in the vertical plane. So this is actually the meaning of pre-coding indexes or matrix, that all these beams the user can select out of them the best beam for him. Now let me explain this with another clear example of how the user would be measuring the CSI-RS and reporting the PMI information, and how the GMB will allocate the traffic channels. Assume now you have 3 users, user 1, 2, and 3, or the same user in different location or moving or whatever. Okay, so this user, for example, is here. This is located here. This one located in the same, but in the same horizontal, but in the vertical. In the same vertical, all of them in the ground, but in the same different in the same vertical, but the horizontal plane is different. And this one, for example, is staying in the top building or high-rise building. Okay, so now what will happen? All these users will go and measure the CSI-RS non-zero power resources and CSIM, which is related to the interference management CSI-RS. So this is the first step. The user will be measuring the CSI-RS in order to obtain these pre-coding matrices to find the best PMI for each one of those. What is the best PMI, and need to report this information in the uplink direction. So once the user, all these users being decoding or reading the CSI resources, here I'm assuming having 8 ports. So now there will be a CSI report being reported from those users to the GMB. So as you can see here, the channel state information, which is CSI-RS, as highlighted before, this is including the CQI information, PMI information, and also the rank, and also multiple other information, but at least this is the core information you need to know. So now assuming that user 1 is telling him, okay, my CQI is 14, forget about it for now, and PMI I11 is presenting the horizontal direction, the horizontal beam. So it's telling him I'm at beam, I need beam number 7. And here is telling him BMI I12 is telling him my vertical is 0. I'm in the ground. So I need the beam to be in this direction, for example. So this is what will happen. Here the GMB, once it receives the CSI report, it will start doing the beamforming implementation through calculating this. If you remember in the previous formula, which is called the co-phasing and this PMI reporting, it will calculate the beam direction. So what will happen? As you can see here, is reporting the traffic beam from I11 equals 7 and I12 equals 0. Then this one, it's 7 and 5, which is related to the user 2. Here 5, because this is in the vertical plane, is staying in higher vertical direction. So now the GMB will changing this one to the upper deck. So this is dynamically happen based on the feedback. And the same for user, this is in different horizontal direction, so he need report another I11, but I12 expected to be 0 as it is because he's still in the ground. So this one will be reporting I13 and I12 equals 0. So now the beam will be allocated in this direction. So just to summarize, the code book, especially type 1, this like by indicating the best pre-coding matrices, which is being applied by GMB to maximize the SNR or signal to noise ratio, and the user need to measure the CSI-RS resources. The first thing the user will do, you'll measure the CSI-RS to estimate the downlink channel characteristic. Then the second step, the user need to report this information into the GMB in the uplink direction, which is through the CSI report, the channel state information, which is covering different information such as CQI, rank indication, and PMI, pre-coding matrix, which is covering information related to the I11 and I12 and even the co-phasing as we highlighted before. Then once the GMB receives this information, it will start calculating the weight vector to try to adjusting the beam towards those particular user based on the information being provided and do a more directed beams in terms of traffic beams, which is the physical downlink shared channel as we highlighted here before. And again, non-zero power CSRS. This is, as I mentioned before, this is something controlled. You can even increase it to 32, so you will have more overhead here, but also this is giving more advantage. The user can have more code box to select out of them, and also might result in more wider beam. So as I highlighted before, there is always a trade-off between different configuration and so on. Before going to the codebook type 2, I would like first you to before going to codebook type 2 explanation, which is more appropriate for the multi-user MIMO, I would like to take you through the U capability check, how to check the users, how many ports being supported, because at the end, the number of ports, for example, assume you make it for 32, you might end by that you find that some of the users cannot read 32 CSR resources, maximum supporting 8 or 16. Again, the network or vendor might have a deployment to do this dynamic, even if it's 32. If you receive 30 from the user that is not supporting 32, still it can do a dynamic change to transmit only CSRS, because CSRS is kind of a dedicated resources and coming only for per user demand. So, but this is the first part. We'd like to check how to check the capability of the CSI-RS maximum number supported of CSI-RS ports. Also the codebook panel type 1 and type 2. Type 2, I will be showing along with the U capability check and so on. So let's go to the U capability to see what we can find there. So here from the capability check, as you can see here, you can see that I have highlighted into two different parts here. The first part here related to the whether the user is supporting this so-called non-zero power for CSRS interference management, IM. Yes, this one, for example, showing supported. And the most important, which is more relevant to our subject, it's related to the codebook parameters. This is actually reported in the U capability information under the codebook parameters here. You can see that he's saying that here I'm supporting only type 1 single panel, and I'm supporting maximum number of CSRS ports up to 16 only. I cannot take 32. So if even you allocated me 32, this might result in problems for the user itself. So this is like an information you need to confirm as well. You can do inside in your network, confirm how many users supporting this and this, and you can confirm with your network implementation whether it's supporting a dynamic change or not, because assume in this case you are doing 32 CSI ports in the configuration point of view, and on the same side the network is the user is not supporting, so this might cause a problem. So this is you need to check. Again, before going to the codebook type 2, I would like to take you through the RRC reconfiguration message to show you how to check the network configuration from the RRC configuration and what it means by CSI resource set ID and the CSI resources and all this kind of information. This is a very interesting example here. I'm assuming this example about the codebook type 1. I'm assuming, for example, here you have a CSI-RS beamforming. You have two beams from the CSI-RS beamformed, and each of those beams having maximum 8 CSI-RS ports. The one. So the user would be maximum measuring 8 CSI-RS ports, but as you can see that you have only two beams. So for example, assume this is your configuration in the current network. You have a beamformed or pre-coded CSRS into two beams, as you can see here. So you need to confirm whether this is really applied for the network or not. How to confirm that? Assume that you are checking any drive test logs and need to confirm. So you go through the RRC configuration message. The first step you'll find here, you'll find something called CSI-RS. Let me zoom in here to move one by one. The first thing you'll find here, you'll find something called CSI report configuration. You will search for you will find a different resource set IDs. For example, one for the resource for channel measurement and one for CSI-M resource for interference, for example. So, for example, here our main is to look into the resource for channel measurement, because at the end the user is measuring the non-zero power, which is used for channel measurement in order to find the PMI reports and these kind of things. So you will refer to the resource for channel measurement. So the first one. So this is the report config ID. You'll find this one, for example, showing as 10. Then the next step, you need to go through the same message. You'll find it all of them near to each other within the RRC configuration message. You'll find something called CSI resource configuration. So under the CSI resource configuration, you need to open this one. You need to search for this number 10. So you'll find CSI resource configuration ID here. This was the configuration ID 10, right? So this one equivalent to 10. So this is your configuration ID. Then you'll find that this one is equivalent to, under the non-zero power CSI-RS SSB, equivalent to non-zero power CSI resource ID, which is 10 here. So this is equivalent to non-zero power. Then the next part you would like to check here, you will move towards. Before going to the second part here, I would like to highlight that under that part here, you'll find that under this, again, let me zoom in here. Under the report config ID, you'll find something called codebook configuration, type 1. Type 1 single panel, number of antenna ports, N1 and N2. You remember N1 and N2? And this N1 and 2 is saying it's 4.2. This means the current configuration is 4 and 2. Okay, this is the current configuration. So now you just define what is your 4 and 1, sorry, 4 and 1. This means you have in the table, if you remember in the previous table, you have N1 and 2 representing 4 and 1. Okay. This kind of restriction thing I can explain later on, but this is the main idea. You'll find it here under this message. So they will refer to 10. Then you move to the next one. You'll find this one under the CSI resource config. It's under 10 here. Then you will go and search under CSI measurement configuration. All of these is near to each other. You'll find it on top of each other. Then you'll find you like to look into the non-zero power resource set ID 10. How many resource set ID under this resource set? How many resource ID we have under this resource set? Okay. So for example, here you have a resource set ID number 10. So you need to know how many CSI-RS resources. As I mentioned here, we have two CSI resources because this is explaining as two narrower beams or two beams. So this is supposed to be that GMB supposed to transmit two CSI resources under one resource set ID, which is referring to the non-zero power. So your resource set ID is referred to non-zero power. Then you will go to here and you find the non-zero power CSI resource set ID 10. Under this part, you'll find non-zero power CSI resources. So under 10, you'll find two resources ID. Resource set ID. Under resource set ID, you have two resources, which is explaining that each one of those will have a different configuration. I'm expecting now each one of those should have 8 ports, right? So I will go again, number 4. I'll go under the non-zero power CSI resource ID. This one was ID 28. You'll find under each of those, you'll find one for 28, which is number 28, and one for 29. This will be showing the configuration for both of them. For example, here it's showing here this is the frequency domain allocation. So based on that part, you can map it. This is coming at which symbol in your frame. I have a video explaining this allocation in details. If you would like to go, I will share it in the video description as well. And here it's showing that the configuration of the network now is 8 ports. And here also the CDM type, something called FD CDM2, and the density means coming in frame as one time only. And this is just highlighting what is the frequency band and so on. I have a video explaining all of this information, how it's being allocated and how you can visualize it as well to identify how many ports, how many CSI resources, so the user will understand where he's supposed to read the CSI resources. And also you can do bar posting or not for the CSIS. This is based on your new preferences. And this is also explaining that the CSI-RS resources will be transmitted by GMB, for example, every 40 slots, which is if you have 40 slots in terms of TDD, this means every 20 milliseconds. So the UE now will know that he needs to go and measure the CSI resources each 20 millisecond at this particular frequency domain or time domain based on this information. So this is how you can configure or confirm your parameters in the network. Here I would like to explain the same concept for the codebook, but type 2. As I mentioned, type 2 is more used for the multi-user MIMO. I will explain why it's being mainly used for multi-user MIMO, but this actually have a more limited pre-coded matrices, as you can see in bottom left here. This is the only table we have. But anyway, forget about this table in time. Let me explain what is the main differences compared to the other one, which is codebook type 1. I just added the codebook type 1 in the bottom left here just to do a comparison, but let me first explain. So this is actually a kind of a similar idea. Initially, the GMB have a number of transmitted beams here, as you can see, total beams at the GMB side. This is again based on your configuration, CSI-RS reports, and 1 and 2, or 1 or 2, and so on. Then the GMB initially will be selecting a group of beams. Let's assume 4 beams, okay? Then in this case, the user in this time will be selecting additional information. For example, last time here he was selecting only the best beam, right? Only one beam. This time he will selecting 4 beams out of whatever beams being transmitted. Assume 4, he will be selecting 4. So this is the first part. The BI here, it will be BI. He will be selecting, for example, from B0 till B3. Okay, I0 till I3, or I0 till. So this is like the BMID. BMID, the user will be selecting all the 4 beams, but this time the user will be reporting not only the BMI I11 and I12 for all these beams, but he will be reporting 2 additional information, or 1 additional information. Last time he was reporting the best beam, only a single beam here, as you can see in the bottom left here, and the co-phase selection, right? What kind of the co-phase or the angle of this kind of beam, or which is both identify his angle of arrival, AOA. While this one is selecting 4 beams and also selecting the co-phasing as well for each of those beams, telling him I need this at this direction, I need this one at this direction, and this is the direction of the beams. This is the best 4 beams I have received, or I'm being able to receive. But again, this is required to maximize the multi-user MIMO, because based on this information, the GNB will have a much higher information about all the beams which expected to be served the user, so he can do something called amplitude scaling. Again, the user would be reporting something called amplitude scaling, telling him out of the 4 beams, the best beams which I have it here, it's beam number, for example, the one here, which is this one. I need this one to have the highest power at this particular beam. For example, if you read into the bottom figure here, it's saying that in R type 2 codebook design, this is amplitude scaling, which is the alpha value, which is a new added compared to the previous examples we have reported before. You can see here, for example, it's saying that the alpha value refers to how much power is assigned for each of the selected beams here, right? So this is determined how strongly each beam contribute to the final combined signal. So here I assume, for example, the alpha here is 1. So this means the full power. And alpha 2, for example, is than 1, which is, for example, this one. I need less power in this direction, so I need to reduce the power in this direction. And also for the remaining alpha 3 and alpha 2. So this here is just explaining that the full power I needed in this beam, while those I need to reduce the power, for example, in this particular direction. So the main idea here now, the GMB will have a rich channel representation, which can enable the multi-user MIMO, because now it knows all the beams which serving this particular user, so it can do this kind of multi-user MIMO to avoid this kind of interference between different beams and so on. So as a summary here, again, the main idea here, that this is reported additional information which can support the multi-user MIMO implementation, and this additional information will increase the overhead for sure in doubling. And again, the rank is limited to 2, as we mentioned before, as a maximum 2. So again, first of all, there will be a beam group selection, and the user this time will select multiple beams from a predefined set. For example, here he selected 4 beams. and in the type codebook one, he selected only the maximum one. Then he will do something called amplitude scaling. Each selected beam will get a different weight, as we highlighted here, and it will adjust the strength for that part. Then there will be a co-phasing and linear combination. Each one will have a different, for example, direction. And again, this is very helpful for the multi-user MIMO. It will have more efficient and distributing power across different beams. And also this will improve the spatial separation in general between the users, as I highlighted. For the capability and this kind of things, you can check it from the same information we have highlighted previously in codebook tag one. Since we have already crossed 1 hour, so I will shift to the SRS part along with the next session, which will be about the SRS and physical downlink command control channel beamforming, as well both of those. And I will try to also cover the beam management and the beam failure detection in the next session as well. Then we'll be ending by the uplink beam management. That's it for today's session. I hope if you like the session, just to drop a comment and to share it with your friends. And see you next video, and thank you very much.